Welcome to this class. Today we want to tackle infrared and microwave spectroscopy. So vibrational spectroscopy, if we talk of vibrational spectroscopy, remember harmonic oscillator. And generally this is the formula, the quantum version of the classical oscillator or the spring. So if Vm here denotes natural frequency of the oscillator, then we have K here that denotes Hooke's law force constant. Then we have V, which is the vibrational quantum number. You can be able to see it here. Then we have H, which is well known Planck's constant. Then mostly V must be a whole number. V must be a whole number. Remember, most of these energy are quantized. So that means also you can get the energy. If you need to get the energy, you will reorganize this formula to this. Energy is equal to Planck's constant times the natural frequency of the oscillator, which gives you can expand it to this formula here. And then if you want to get wave number, you can actually use that formula, and you can be able to get, so where the Planck's constant over 2 pi gives you 5.3 times 10 raised to power negative 12. Then now these ones you can get the Hooke's law force constant, and then you can also get the mass, and this is mass 1. If you remember that our two masses connected by a spring, so m1 times m2 over m1 plus m2. Then the potential energy function is can be gotten as down here, provided down here. Vibrational spectroscopy, we are still continuing. The potential energy of vibration fit the parabolic function fairly well, only near the equilibrium internuclear distance. So you can be able to see, naturally you would expect that the displacement will be that uniform, but in reality it's not the case. So you can be able to see in this other diagram that there is what we call an harmonic oscillator model, which is the more accurate description for the overall motion. Naturally, you would expect this to be the the way the two springs behave, but the reality is there will be some collision, there will be some disturbances leading to an harmonic model. So anharmonic corrections. Anharmonic motion, when the restoring force is not proportional to the displacement, more accurately given by the Morse potential function than by the harmonic oscillator equation, primarily caused by Coulombic repulsion as atoms approach. And you can be able to see the correction here, where dE here is the dissociation energy, and the A that is provided here can be gotten by this particular formula. So effects at higher quantum numbers, change in energy gets smaller, and the change in vibrational energy is either plus or minus 1. Selection rule can be broken. So those are just some of the things. It means, if as we will discuss later, the absorption band of IR, you will realize that there are some things called overtone bands at higher frequencies than IR. So those are due to such that have been discussed. Then rotational vibrational spectroscopy of condensed phases appear as bands rather than lines. Naturally, we expect them to appear as lines, but that is not the case. When the vibrational spectra of gaseous molecules are observed under high resolution conditions, each band can be found to contain a large number of closely spaced components resulting from rotational energy levels. So that is very key, very important. rotational energy levels can be described as follows. You can be able to see rotational energy or frequency can be collected as follows, as I have provided there. So the rotational constant, this B, we call it the rotational constant. We can also work it out using this particular formula. The centrifugal distortion coefficient can also be provided like that, where as we all know, C is the speed of light, K is the Hooke's law, force constant. Then we have RO, RO here, that is the vibrationally average bond length. Then we have mu, that is the reduced mass. Then we have H, which is the Planck's constant. So you can be able to see here, for a molecule with n atom, the number of vibration modes is, for a linear case, it will be 3n minus 5 modes. For nonlinear, it will be 3n minus 6 modes. So you can see here, if we have molecules that are, if these ones are the same, if there is a symmetric vibration, then it is going to be IR inactive. But if we have asymmetric, then we are going to have change in dipole, and means that it is IR active. If we have scissoring, then it means that there is going to be change in dipole, and it is going to be IR active. So types of vibration will be stretching and bending. Example, if we have carbon dioxide, we remember it is having 3 molecules, so it will be, because it is linear, it is going to have 3 times the number of molecules, which is 3 minus 5. So 4 normal modes are possible. Higher active modes require molecular dipole moment changes during rotation and vibration. Then instrumentation for vibrational spectroscopy. Remember we said that earlier we've been using dispersive methods of IR, where scanning of wavelengths using a grating, common example are double beam like a spectrometer, discussed in optical electronic spectroscopy. So here the instrumentation, you have radiation source, then it goes through the sample, then a wave is selected, and then that wave is transferred to the detector, which is a transducer. And here it is very important to remember that IR has a heating effect, and that's the detectors are made in such a way that they can be able to detect change in temperature. But because this scanning of wavelength is very tedious, and it means if you want to analyze a lot of samples, there will be a problem, and most of our detectors cannot be able to receive all the frequencies at the same time. The frequencies of this particular radiation has to be modulated, and that's why we come up with the Fourier transform methods based on interferometry, a method of interfering and modulating IR or infrared radiation to encode it as a function of its frequency. So immediately we have a radiation source, it goes through an interferometer before it goes through the sample, and then directly to detector. There is no wavelength selector. Then majorly we do IR absorption spectroscopy. IR emission spectroscopy is not much used for chemical analysis. The sample must, for us to achieve IR emission, the sample must be heated to a temperature much greater than its surrounding, which leads to destroying of molecules. So IR emission is widely used in astronomy and in remote sensing applications of heated materials. So that's where we restrict their use. Then generally this is how interferometer is, the structure of an interferometer, what we call the Michelson interferometer, the product of famous physics experiments. So we might not really dwell here because it needs a whole lecture. Produces interference pattern from monochromatic and white light. So you can be able to see the kind of interference, can be able to see. So much on interferometer. We are not going to really dwell here, but for monochromatic radiation, the interferogram looks like a cosine curve. It looks like a cosine curve. For polychromatic radiation, each frequency is encoded with a much lower amplitude modulation. The relationship between frequencies can be worked out using this formula, where F here is the frequency, and then Vm is the mirror velocity in centimeter per second. Then we have speed of light, centimeter per second. Then we have V, the frequency of the radiation. Then the design, as you can be able to see, it is possible to build a detector that detects multiple frequencies for some electromagnetic radiation. For example, in ICP OES, which has the CCD detectors. In UVVs, we have the diode array detectors. This is the charge couple detectors. Fourier transform IR spectrometers are designed around the Michelson interferometer, which modulates each IR individual frequencies with additional unique frequency well suited to the time response of IR detectors. The major problem with IR detectors is that they are not fast enough. So these frequencies have to be modulated so that they can all be detected. So you can be able to see, and you can be able to see that the sample has to, the IR source and the Michelson interferometer are at 90 degrees. Very important, very important. Then just to see majorly what is going on, the conversion from time to frequency domain. So if you have time domain, then we have frequency domain. So you can be able to see there. Yeah, you can be able to see there. Time domain, frequency domain. So IR sampling methods, absorbance methods. Remember we said that water or any hydrogen bond affect IR. So if we are doing the sampling, we have to use potassium bromide, can have sodium bromide, then cesium iodide pellets. I dilute 1% amount of sample in the halide matrix is pressed at 10,000 psi to form a transparent disc. The disadvantage dilution required can cause changes in sample. Then we have MALS, solid dispersion of sample in a heavy oil nozzle. Also here there is a disadvantage, big interference. Then we have salt plates, sodium chloride. For liquids, a drop and a small amount of solids. Sample is held between two plates or is squeezed onto a single plate. Then we have cells for liquid or dissolved samples include internal reflectance cells. Common IR solvents, we have carbon disulfide. You will realize that most of our solvents here are not polar, very less polar. We have benzene, we have chlorohexane, dioxane, we have dimethyl formamide, we have chloroform, we have tetrachloroethylene, carbon tetrachloride. So we can be able to see all that. Then specular reflection, direct reflection of a flat surface where we have grazing angles. Then we have attenuated total reflection being passed through an IR transparent material with a high reflective index, causing internal reflection. Can be able to see that. Then we have diffuse reflection, a technique that collects IR radiation scattered off of fine particles and powders used for both surface and bulk studies. The detectors, we have the thermal transducers. Response depend upon heating effects. of IR radiation. Generally, they have slow response times, typically used for dispersive instruments or special applications. Then we have pyroelectric transducers, insulators which retain a strong electric depolarization after removal of electric field while they stay below their Curie temperature. Then we have the DTGs, deuterated triglycine sulfate, which is also under the pyroelectric transducers. They are a bit fast. They have fast response time, useful for interferometry. Then we have photoconducting transducers. Absorption of radiation decreases electric resistance. Cool to liquid nitrogen temperatures 77 Kelvin to reduce thermal noise. So mid-IR for photoconducting transducers will use mercury cadmium telluride. The near IR will use lead sulfide. Interpretation of IR spectra. General features, remember we said that some of the vibration are specific frequencies. So stretching frequencies are greater than corresponding bending frequencies. Very important to note. It is easier to bend a bond than to stretch it. So of course, stretching frequency will have higher wave numbers. So bond to hydrogen have higher stretching frequencies than those to heavier atoms. So hydrogen is a much lighter element. Triple bonds have higher stretching frequencies than double bonds, which have higher frequencies than single bonds. Very important. So you can be able to see here that the fingerprint region, where we have from 1000 per centimeter, so as we go to 4000 per centimeter, we will realize that the double bonds falls around 1800 to 1500. So for example, they see carbon-carbon bond, there is carbon-nitrogen double bond, there is carbon-oxygen double bond. So that tells you that carbon-carbon double bond has slightly absorbs a bit lower frequency compared to carbon-nitrogen, then lastly carbon-oxygen. Then the triple bond will absorb even much higher wave numbers, where we have carbon-nitrogen double bond and carbon-carbon double bond, triple bond, sorry. Then we said that stretching of carbon hydrogen will absorb a bit higher, and then if we have a hydrogen connected to heteroatoms, for example oxygen, nitrogen, they'll absorb even at much higher wave numbers. So strong IR often correspond to weak Raman bonds and vice versa. So most of the compounds that are Raman inactive are IR active and vice versa. So for example, we can be able to see just a summary. Around this we'll find the stretching of hydrogen attached to carbon and heteroatoms. Around this range we'll find, so generally what we've discussed there, and it is good to note that this is the fingerprint region. This is good to note that this is the fingerprint region. So application of near IR spectroscopy heavily used in the process chemistry and material identification is amenable to quantitative analysis, usually in conjunction with chemometrics. While not a popular qualitative technique, it can serve as fast and useful quantitative techniques, especially using diffuse reflectance. Accuracy and precision in the range 2% range. Example is online reaction monitoring, food, agriculture and pharmaceuticals, moisture and solvent measurements and monitoring, and solid blending and solid state issues. So you can be able to see near IR. You can be able to see. Then we have for an example of near IR spectrum of acetone. You can be able to see.